Well, hello. My name is Nicolás Jaime. My partner's name is Alejandra Pedraza. And today we are going to talk about the Butterworth and Chebyshev filters. First, I'm going to start with the Butterworth filter, and then Alejandra is going to explain the Chebyshev filter. To begin with, we are going to talk about the life of Stephen Butterworth. Stephen Butterworth was the first engineer to use the Butterworth filter in the 20th century. He said that he wanted the filter to not only completely reject the unwanted frequencies, but also have sensitivity for the unwanted frequencies. That means that he wanted to show an uniform curve for the wanted frequencies. So in the next paragraph, we see that he wanted the equation to be 1 radian by second divided to the square root of 1 plus e squared. And in the transfer function, we see that this is the equation that he modeled for this Butterworth took to be a shift. He wanted to be basically a uniform curve all the time, and he wanted the approximation to display a transmission that decreases in a constant form with all the transmission zeros being near the infinite, meaning that the filter works for every pole. So if you wanted to um, do every transform or every circuit in this example, you can do it because it has the zeros being near infinite. So the magnitude function for an n order with the passband is given by the equation that we have here in the presentation. So in the next, we see that in the border of the suppressed band, W equal equals omega s, the attenuation of the filter will be given by the equation, this one, that it's minus 20 log equals 1 radian by squared plus e squared omega g divided omega c equals um, by 2n equals 10 log uh, in parentheses 1 plus e um, by w by wc at 2n. So then we can see that Butterworth solved the equations for 2 and 4-pole filters, showing that the latter could be cascade, so we can put various filters in one, and then we separated but vacuum tube amplifiers to enable the constructor of high-order filters despite the inductor losses. Then, in the next presentation, we see the natural modes. Ah, we can also in the last equation we can also confound the E using the equation of A max, but changing the order. And then we can see in the next one, that is the minus 20 log, that the maximum deviation in the transmission of the band pass occurs only in the border of it. The first derivative of 2n minus 1 of the function transfer could be proven in relation of w. R zeros in w equals to 0. This property makes plane near W0, which means that when the thing is W0, it's like a plane thing. When um, when the zeros became W equals 0, and this flatness degrees of the band increases when the end order increases. If it increases, a lot of the response will look like this, like a brick wall, like a straight line. And in the border of the suppressed mount W equals Ws, the attenuation of the filter will be given by the equation of that what we see that that was minus 20. Well, I already explained. The natural modes can be found in the next one in the circle of radius WP un by one the by at 1 divided by n, and they are spaced by the same angles pi by n. We can see in the next four that in the four circles that the natural modes are divided like this, and we can find different equations using this type of circles. Due to all the natural modes have the same distance to the origin, because all the modes have the same distance to the origin, like the same radius. They all have the same frequency. W0 equals to WP by 1 divided by E at 1 by N. That's how the natural modes work in this equation. Where in the next one, in the final equation, like the function transfer of the Butterworth, they have the same values. Um, like we see already, they have the same values of frequency. Where k is the constant equal to the the CD gain required in the filter. So that was all the Butterworth explanation for the Butterworth filter. So we are going now with my partner Aleja. Aleja, thank you.
Hello, I'm going to tell you about the Chebyshev filters, name given in honor to the Russian mathematician P.L. Chebyshev, who used it in the 19th century this function in the study and construction of steam machines. Exhibits a heavy response in the passband and a constant decreasing transmission in the suppressed bandwidth. The total numbers of heights and those of the bandwidth pass is equal to the filter's order n. All the transmission series begin near infinity, meaning that this filter works for every pole. The attenuation for this filter can be found using the given equation. Finally, the transfer function of the filter is this, where k is constant equal to the CD gain recreated in the filter. Thanks for your attention. The parameter determines the passband ripple according to equation of A max, and the E parameter determines the core of the passband width in accordance with the equation can you see now. The attenuation achieved by the Chebyshev filter at the stop point H W equal to Ws is found using the equation. Can you see the A of the Ws? Finally, the transfer function of the Chebyshev filter can be written as the T of S, where key is the CD gain that the filter is required to have. The Chebyshev filter provides a more efficient approximation than the Butterworth filter, thus for the same order and the same Emax, the Chebyshev filter provides greater stop-band attenuation than the Butterworth filter. Alternatively, to meet identical specification on requires a lower order of the Chebyshev than for the Butterworth filter.